Good morning all of you. Today I am going to make an audio recording for visually impaired student of Organic Chemistry book of Dr. J. M. Sehgal modern book. Name of the chapter is Mechanism of Organic Reaction. Introduction. During the study of organic chemistry, we come across numerous reactions which the organic compounds undergo. As we study these reactions, we not only want to know which reactant give rise to which product, but we are also interested in knowing how it happens. Do the reactant change directly into the product in a single step, or does the reaction take place by several steps through the formation of reactive intermediates? The complete description of how a particular reaction takes place is called mechanism of the reaction. It tells us which bonds are broken, in what order, and which bonds are formed and in what order. It also tells us what kind of intermediates are involved and what are the relative rates of different steps. We shall now consider some important notation and basic concepts involved in the study of organic reactions and their mechanisms. Important notation. Reaction of organic compound involve the breaking and making of covalent bonds and the movement of electrons from one side to another. To indicate these changes, certain notation involving the use of different kinds of arrow have been adopted as described below. First, curved arrow notation. It is very useful notation in which a curved arrow indicates the movement of electrons as bond in the reactant are broken and new bond in product are formed. It means that an electron pair moves from the atom at the tail of the arrow to the atom at the head of the arrow. This is illustrated below with the help of reaction between water and hydrogen chloride. The electron pair moves from oxygen of H2O to H of HCl. The bond between H and Cl breaks and the electron pair moves to Cl. Give rise to the electron pair that moves from oxygen form a new bond with hydrogen to give H3O positive ion. The electron pair of HCl bond goes to Cl to form Cl negative ion. Similarly, the reaction between acetylene and amide ion NH2 negative to form acetylide ion CH triple bond C negative and ammonia may be shown below. Second, half-headed arrow. As will be described in section 2.3, sometime a bond between two atoms break in such a manner that each atom gets one electron of shared pair. To represent this type of symmetrical bond breaking and bond making, half-headed arrow are used as shown ahead. It may be noted that a half-headed arrow is used for showing the movement of single electron, while a full-headed arrow is used for a pair of electrons. Third, double-headed arrow. This type of arrows are placed in between the various canonical structure of a substance which exhibits resonance. This is to indicate that the actual structure is hybrid of these structures which are hypothetical and not real. For example, double-headed arrow are placed between the two major canonical structure of benzene to indicate that the actual structure of benzene lies in between these two structures which do not have a real existence. Type of bond cleavage. Reactions of organic compound almost invariably take place through the breaking and formation of covalent bonds. Depending upon the nature of given organic compound, the nature of attacking reagent and the reaction condition, a bond between two atoms of a molecule may be cleavaged or broken into different ways, producing different type of reaction intermediate. The different possibilities are illustrated below by considering a covalent bond between two atoms A and B. First, homolytic cleavage or homolytic fission or homolysis. This involves the breaking of covalent bond in such a way that each atom separates with one electron of shared pair. This leads to the formation of highly reactive neutral particles containing odd or unpaired electron and known as free radical. It may be seen that the homolytic cleavage of bond is shown by using half-headed arrow in the pairs. Second, heterolytic cleavage or heterolytic fission or heterolysis. This involves the breaking of a bond in such a way that both the electrons of the shared pair are carried away by one of the atom. First is shown heterolytic cleavage when A is more electronegative than B, and second reaction is shown heterolytic cleavage if B is more electronegative than A. Heterolytic fission led to the formation of charged or ionic species, one having a positive charge and the other having negative charge. If both the shared electrons are taken away by A, it would be converted into an anion A negative and B into a cation B positive. On the other hand, if both the shared electrons are retained by B, it would change into an anion B negative while A would form a cation A positive as shown above. Quite often, the ionic species formed by heterolytic fission bears a positive or negative charge on carbon. Such ionic species are known as carbocation, earlier called carbonium ion, or carbon ion, according as carbon carried positive or negative charge. It may be mentioned that if a particular covalent bond can undergo either homolytic cleavage or heterolytic cleavage under different conditions, the bond dissociation energy for homolytic cleavage is considerably different from that for heterolytic cleavage. In general, the values for homolysis are low while they are quite high for heterolysis. For example, the bond dissociation energies for CCl bond in CH3Cl for homolytic and heterolytic cleavage are 351 and 949 kJ mole inverse respectively. Homolytic fission CH3Cl homolytic fission give rise to CH3 radical plus Cl radical. Heterolytic fission CH3 single bond Cl double headed arrow to Cl give rise to CH3 positive plus Cl negative. Reaction intermediate. The student is already familiar with the fact that in organic reaction, the starting substance seldom change into the product directly in one step. On the other hand, the reactant first change into intermediate substance called reaction intermediate, which ultimately yield the product. The reaction intermediates are generally very unstable and reactive substance which cannot be even isolated. We will now briefly deal with the main reaction intermediate which are often come across in organic chemistry. Carbocation, earlier called carbonium ion. First, what are carbocations? A carbocation is a cation in which the positive charge is carried by a carbon which has only 6 electrons in its valence shell. For example, CH3 positive and CH3CH2 positive are simple carbocation known as methyl cation and ethyl cation respectively. A carbocation may be assumed to be a fragment of a molecule from which an atom or group singly bound to a carbon get removed along with the pair of bonding electrons. For example, if a bromide ion is removed from a molecule of tertiary butyl bromide, tertiary butyl cation would be formed as shown below. Tertiary butyl bromide give rise to tertiary butyl carbocation plus Br negative. Carbocation are very short-lived and highly reactive species. The reactivity of carbocation is due to their tendency to complete the octet of electron-deficient carbon. As a result, carbocation undergo a variety of reactions. Second, formation of carbocation. Carbocation can be generated in many different ways. Some of the reactions in which they are formed are given below. First, direct ionization. The carbon halogen bond CX in many organic halide degenerates carbocation in the presence of highly polar medium. For example, tertiary butyl chloride give rise to tertiary butyl cation plus Cl negative. Allylic chloride give rise to allyl cation plus Cl negative. This method of a particular importance in the formation of relatively more stable carbocation. Second, by the protonation of unsaturated compound. Unsaturated compounds such as alkenes, carbonyl compound and nitrile furnish carbocation on treatment with proton donating solvents. For example, RCH double bond CH2 double bond is breakdown react plus H positive give rise to RCH positive CH3. Similarly, C double bond O plus H positive give rise to C positive OH. C triple bond nitrogen plus H positive give rise to C positive double bond NH. Third, from compound containing an atom with lone pair of electrons. When an organic compound having lone pair of electrons on an atom, especially oxygen, is treated with an acid, protonation of this atom takes place. This is followed by the elimination of a simple molecule containing this atom to furnish a carbocation. For example, alcohol plus H positive give rise to protonated alcohol, give rise to carbocation plus H2O. For example, ether plus H positive give rise to protonated ether, give rise to carbocation plus ROH. Fourth, by the decomposition of diazonium salt. For example, primary amine in the presence of HNO2 give rise to diazonium cation, give rise to carbocation plus N2. Fifth, by the action of superacid on alkyl fluoride. For example, RF plus SbF5 give rise to R positive plus SbF6 negative in the presence of FSO3H. Note, the term superacid is used for some exceptionally strong acidic solutions such as SbF5 plus HF or SbF5 plus FSO3H dissolved in SO2 or SO2ClF. Structure of carbocation. The positively charged carbon of the carbocation is in sp2 state of hybridization. The 3 sp2 hybridized orbital which lie in the same plane are involved in the formation of 3 bonds with other atom. The unhybridized p orbital remain vacant. Thus the carbocation has a flat structure as represented on the right hand side. The bond angle around the positively charged carbon is nearly 120 degrees each. Classification of carbocation and their order of stability. Carbocation are classified as primary, secondary or tertiary according as the carbon bearing the positive charge is primary, secondary or tertiary in nature. In addition, the methyl ion having only one carbon is regarded as a special case. Methyl cation, ethyl cation primary, isopropyl cation secondary, tertiary butyl cation tertiary. It has been established that the order of stability of carbocation is tertiary greater than secondary greater than primary greater than methyl. Explanation of relative stabilities of alkyl carbocation. A basic principle involved in discussing the relative stabilities of carbocation is that how does a given factor influence the magnitude of positive charge carried by the electron deficient carbon of carbocation. It is apparent that any factor which tends to disperse the positive charge by distributing it over the rest of the molecule stabilize the carbocation. In contrast, any factor which tends to intensify the positive charge destabilize the carbocation. The relative stabilities of alkyl carbocation are given above can be explained in term of inductive effect and hyperconjugation in term of the above principle. First, inductive effect. This is the main factor operating in determining the relative stabilities of carbocation. As is well known, the alkyl group are more electron releasing than hydrogen. As such, an alkyl group attached to the positively charged carbon of carbocation tend to release electron towards that carbon due to its plus I effect. In this way, the positive charge on the carbon get dispersed. This dispersal of the charge stabilizes the carbocation. Now, the more the number of alkyl group, the greater the dispersal of positive charge and therefore more the stability of carbocation. That is why a tertiary carbocation having 3 alkyl group attached to the positive carbon is more stable than a secondary carbocation with 2 alkyl group. The secondary ion in turn is more stable than primary carbocation having only 1 alkyl group. The methyl carbocation does not have any alkyl group and is therefore the least stable. Tertiary carbocation, maximum dispersal of positive charge, maximum stability. Then secondary carbocation, then primary carbocation, and then methyl carbocation, least dispersal of positive charge, least stability. It is quite evident that presence of electron withdrawing substituent minus I effect will destabilize the carbocation by intensifying the positive charge on carbon. Second, hyperconjugation. The concept of hyperconjugation is also to some extent responsible for the observed order of relative stabilities of carbocation. Hyperconjugation can take place here through the overlap of sigma orbital of alpha CH bond of alkyl group and the empty p orbital of carbocation, taking CH single bond C positive to represent a carbocation. In general, delocalization of electron through sigma p orbital overlap may be shown as. Due to this overlap, the delocalization electron bind together 3 atoms, 2 carbon and 1 hydrogen to some extent. In terms of resonance, the above situation may be depicted as. The net result is that in actual structure, CH bond is slightly lesser than a single bond. The carbon-carbon bond has some double bond character, while the positive charge is partially accommodated by hydrogen atom. This partial accommodation of positive charge over hydrogen led to dispersal of charge and consequently stabilized the ion. In methyl carbocation, no such dispersal of charge is possible because hyperconjugation does not take place. In ethyl carbocation 1 degree, which contain 3 alpha hydrogen, the positive charge can be dispersed over 3 hyperconjugation structure, possible in addition to the normal structure as shown below. In isopropyl carbocation 2 degree, which contains 6 alpha hydrogens, there will be 6 hyperconjugation structure possible. In tertiary butyl carbocation 3 degree, which contain 9 alpha hydrogen, there will be 9 hyperconjugation structure possible. As the number of contributing structure and with the dispersal of charge become more, the stability of the carbocation goes on increasing. Thus, the relative stabilities of alkyl cation may be due to the combination of inductive effect and hyperconjugation, although it is usually explained in the term of inductive effect alone. Third, conjugation of positive charge with a double bond or benzene ring, resonance stabilization. The carbocation in which the positively charged carbon is conjugated with a double bond or benzene ring have been found to have extra stability. This have been attributed to resonance effect involving the electron of double bond. For instance, allyl cation is a resonance hybrid of two equivalent structure as shown below. CH2 double bond CH single bond CH2 positive. Resonance sign CH2 positive CH double bond CH2. It is apparent that positive charge of the carbon of carbocation get dispersed over 2 carbon atoms. Hence, the allyl cation acquire greater stability and is found to be more stable than simple alkyl cation. Similarly, benzyl carbocation is greater stabilized by resonance as shown ahead. It is evident that carbocations having more than one phenyl group attached to positively charged carbon would be still more stable. This is because there will be greater dispersal of positive charge due to large number of contributing structures. Accordingly, diphenyl methyl carbocation would be more stable than benzyl carbocation because there are 3 more contributing structures. Similarly, triphenyl carbocation would be still more stable. 6 more contributing structures. In fact, triphenyl methyl carbocation is so stable that some of its salts such as perchlorate can be isolated and stored for months. Effect of substituent on the stability of benzyl carbocation. It can be readily understood that the presence of electron releasing group at the ortho and para position of the phenyl group with respect to the position where C2 positive group is attached will tend to further stabilize the benzyl carbocation. On the other hand, the presence of electron withdrawing group at these positions would have the opposite effect. For example, the order of stability of the following substituent benzyl ions is CHO3 has plus I effect, NO2 has minus I effect. Fourth, instability of vinyl and phenyl carbocation. The carbocation in which the positive charge is carried by a doubly bonded carbon atom such as vinyl cation CH2 double bond CH positive and phenyl cation C6H5 positive are found to be highly unstable. This is because these ions do not undergo resonance stabilization at all. The reason for lack of resonance is that the vacant orbital of the carbon carrying the positive charge is perpendicular to the double bond and therefore it cannot participate in resonance. Determination of relative stabilities of different kinds of carbocation. It is evident from the above discussion that the stability of carbocation is primarily related to the dispersal of charge carried by the positively charged carbon. The dispersal of charge may be due to the inductive effect, hyperconjugative effect or resonance effect as explained above. The relative stabilities of different kind of carbocations can be measured in terms of heterolytic bond dissociation energies, leading to the formation of carbocation. Ax give rise to A positive plus X negative. On the basis of these values, the decreasing order of stabilities of some of the common carbocation are given ahead. Tertiary butyl greater than benzyl, greater than isopropyl, greater than allyl, greater than n-propyl, greater than ethyl, greater than vinyl, greater than phenyl, greater than methyl. It may be pointed out, however, that benzyl isopropyl and allyl carbocation are almost equally stable. Similarly, vinyl, phenyl and methyl carbocation have nearly the same stability. Sixth, rearrangement of carbocation 1,2 shift. An important feature of carbocation is that they can undergo rearrangement reaction to form more stable carbocation. These rearrangements involve the shift of either a alpha hydrogen or alkyl or aryl group along with its electron pair from an adjacent carbon to the positively charged carbon. Such shifts are known as 1,2 shift. The shift of hydrogen is known as 1,2 hydride shift, while that of alkyl group is known as 1,2 alkyl shift. The cation thus formed contain a new charge center and is more stable than the original carbocation. For example, 1,2 hydride shift. N-propyl cation 1 degree give rise to isopropyl cation 2 degree more stable in the presence of 1,2 hydride shift. Second, 1,2 methyl shift. Neopentyl cation 1 degree in the presence of 1,2 methyl shift give rise to 2-methyl 2-butyl carbocation 3 degree more stable. The rearrangement reaction of carbocation are discussed in detail at later stage in the book. Carbanion. First, what are carbanion? A carbanion is an anion in which the negative charge is carried by a carbon. This carbon has 3 bonds with one or more other atom and possesses a lone pair of electron. For example, C negative triple bond CH is a simple carbanion known as acetylide ion. A carbanion may be assumed to be a fragment of a molecule when one of the atom or group singly bound to a carbon is removed without the bonding pair of electron. For instance, removal of a hydrogen of methyl part of acetaldehyde molecule as a hydrogen ion result in the formation of carbanion as shown below. Acetaldehyde give rise to carbanion plus H2O. Carbanion constitute highly unstable and one of the most reactive reaction intermediate in organic chemistry. They are very frequently involved in the reaction of aldehyde, ketone, esters, etc. Their reactivity is due to the fact that the negatively charged carbon in them has got a lone pair of electron. It has a strong tendency to donate this pair to some electron deficient species. Therefore, carbanion easily participate in many reactions. Second, formation of carbanion. There are two main methods by which carbanion are generated as given below. First, by the dissociation of a molecule in which an atom or group singly attached to carbon leaves it without the electron pair. That is, CH give rise to C negative plus H positive. In most of the cases, the leaving group is a proton and hence a base is required to facilitate the process. Thus, the formation of carbanion is an acid-base reaction. Since the presence of electron attracting substituents such as carbonyl, cyano or nitro group on the carbon carrying the hydrogen make the hydrogen relatively more acidic and therefore more easily removable as a proton, the generation of carbanion from such compound play an important role in organic chemistry. For example, OH negative plus CH3 CHO give rise to CH2 negative CHO plus H2. C2H5O negative plus HCH2 NO2 give rise to CH2 negative NO2 plus C2H5OH. To remove a proton from a hydrocarbon, very weak acid, very strong base such as sodamide in liquid ammonia has to be used. For example, CH triple bond CH plus NH2 in the presence of liquid ammonia give rise to CH triple bond C plus NH3. But aromatic compound of the type triphenyl methane generate carbanion very easily in the presence of a base. Triphenyl methane plus OH give rise to triphenyl methyl anion plus H2O. It may be pointed out that apart from proton, other leaving groups are also known to lead the formation of carbanion. For example, RC double bond O negative give rise to R negative plus CO2. Second, by the addition of a nucleophile to carbon-carbon multiple bond. But this type of addition occurs only when the double bond is activated towards nucleophilic attack by electron withdrawing group such as a carbonyl, cyano and nitro group. For example, C2H5O negative plus CH2 double bond CH, single bond C triple bond and give rise to C2H5O CH2, single bond CH negative, single bond C triple bond nitrogen. Structure of carbanion. The negatively charged carbon of carbanion is in the state of sp3 hybridization so that the hybridized orbitals are directed towards the corners of a tetrahedron. Three of the hybrid orbitals are involved in the formation of single bonds with other atom while the fourth orbital contains a lone pair of electrons. Thus carbanion have distorted tetrahedral or pyramidal structure as shown on the right hand side, but the bond angle around negatively charged carbon are less than 109 degree 28 minutes. This is because lone pair bond pair repulsion is greater than bond pair repulsion. It must be pointed, however, that in case of carbanions in which negatively charged carbon having the lone pair of electron is in the conjugation with a multiple bond, the carbanion has a plane structure. Some common example of carbanion having planar structure are given below. Allyl carbanion, benzyl carbanion, acetaldehyde carbanion. Classification of carbanion and their order of stabilities. Like carbocation, carbanion are also classified as primary, secondary and tertiary carbanion according as the negative charge is carried up by primary, secondary or tertiary carbon. In addition, methyl carbanion is considered to be special case. Thus, we have methyl carbanion, ethyl carbanion primary, isopropyl carbanion secondary, tertiary butyl carbanion tertiary. The order of stabilities of different classes of carbanion has been found to be methyl greater than primary, greater than secondary, greater than tertiary. Explanation of relative stabilities of carbanion. First, inductive effect. The above order of stabilities of primary, secondary and tertiary carbanion can be justified on the basis of electron releasing plus I inductive effect of alkyl group. Due to this effect, the alkyl group tends to increase the electron density on the negatively charged carbon. As a result, the carbanion become less stable and more reactive towards electron deficient species. Now, the greater the number of alkyl group in the carbanion, the more would be its reactivity and the lesser its stability. Thus, is in keeping with the order of stability given above. It is evident that the presence of electron withdrawing substituent minus I effect such as NO2, Cn, etc. which stabilize the carbanion by dispersal the negative charge on carbon. For example, N2O, benzene ring at the para position, CH2 at the para position negative, P-nitro benzyl carbanion is more stable than benzene ring CH2 negative due to the presence of electron withdrawing NO2 group. On the other hand, presence of group having plus I effects such as R, RO, OH etc. will destabilize the carbanion by intensify the negative charge. Second is hybridization. The relative stabilities of some carbanion can also be compared in terms of hybridization. For example, let us consider the following carbanion: alkyl carbanion, alkenyl carbanyl, alkyl carbanion, sp, sp2, sp3. In hybridization, 50% S character, in sp2 hybridization 33% S character, and in sp3 hybridization 25% S character. State of hybridization of negatively charged carbon and percentage of S character. It may be noted that hybridized orbital having greater S character have relatively more electron attracting tendency or electronegativity than orbital having lesser S character. At the same time, the greater the electronegativity of an atom, it can accumulate negative charge more easily. Therefore, the negatively charged carbon of alkynyl ion can accumulate negative charge more easily, and therefore the alkynyl ion is more stable than alkynyl ion, which in turn is more stable than alkyl ion. Third, resonance or conjugation. As in case of carb-cation, even the carbanion which exhibits resonance or conjugation have extra stability due to the dispersal of negative charge as shown below for alkyl carbonyl. CH2 double bond CH single bond CH2 negative give a resonance sign CH2 negative single bond CH double bond CH2. Similarly, benzyl carbanion is highly stabilized by resonance as shown below. It is evident that the more the number of phenyl group attached to the carbon carrying the negative charge, greater will be the dispersal of negative charge due to larger number of contributing structures. That is why diphenyl methyl carbanion is more stable than benzyl carbanion. 3 more contributing structures. For the same reason, triphenyl methyl carbanion is one of the most stable carbanion. 6 more contributing structures. The carbanion obtained by the removal of alpha hydrogen from carbonyl compound are also stabilized by the resonance as shown below. Free radicals. What are free radicals? A free radical is an atom or group of atoms having an odd or unpaired electron. It is denoted by putting a dot against the symbol of an atom or group of atoms. For example, Cl radical stands for the chlorine free radical, while CH3 radical denotes a methyl free radical. Free radicals are electrically neutral spaces which are usually formed by the homolytic cleavage of molecules in the reaction taking place in gas phase or in non-polar solvent. For example, ClCl give rise to 2 chlorine free radical. Benzoyl peroxide give rise to benzoyl oxy free radical. Due to the presence of odd electron, free radicals are paramagnetic in nature. Free radicals are highly short-lived species. They are extremely reactive, and as soon as a product is formed, they immediately participate in some further reaction. Their greater reactivity is due to the tendency of odd electron in them to get paired up. Second, formation of free radical. There are 2 main methods by which free radicals are usually formed. First, by thermal or photochemical homolysis of covalent bond. For example, tetramethyl lead in the presence of heat give rise to Pb plus 4-methyl free radical. Benzoyl peroxide in the presence of heat give rise to benzoyl oxy free radical plus give rise to 2-phenyl free radical plus 2CO2. Diacetyl in the presence of light give rise to acetyl free radical. Second, by oxidation reduction reaction involving gain or loss of single electron. For example, Rc double bond O single bond O negative give rise to Rc double bond O radical give rise to R radical plus CO2. Third, structure of free radical. It may be pointed out that in case of free radical containing carbon, the state of hybridization of carbon atom having odd electron is not clearly established. However, there is strong evidence to indicate that most of the alkyl free radicals, such as methyl radical, are actually planar. This means that carbon atom carrying the odd electron is in sp2 hybridized state. The 3 coplanar hybrid orbitals are involved in the formation of 3 single bonds with other atom. The unhybrid p orbital, which lies in the plane at right angle to the plane of hybrid orbital, carries the odd electron. The bond angle around the carbon carrying the odd electron is approximately 120 degree each. Fourth, Classification of free radicals and their order of stability. Alkyl free radicals are classified as primary, secondary or tertiary according as the odd electron is carried by a primary, secondary or tertiary carbon atom. But methyl free radical CH3 radical having only one carbon is treated as a special case. Thus, we have methyl free radical, ethyl free radical primary, isopropyl free radical secondary, tertiary butyl free radical tertiary. The order of stability of different type of free radical relative to the alkene from which they are derived is found to be tertiary greater than secondary, greater than primary, greater than methyl. This order is derived from the bond dissociation energy involved in the formation. The lesser the bond dissociation energy in the formation of free radical, the more its stability. To illustrate the above statement, let us consider the homolytic fission of an alkane into an alkyl radical and a hydrogen atom, that is, RH give rise to R radical plus H radical. It is apparent that delta H of such a dissociation process must be equal to bond dissociation energy of the bond between the concerned hydrogen and the carbon of the alkyl group. A study of the delta H of several reactions involving the dissociation of different alkyl to form different classes of alkyl radical showed that the amount of energy required to form various classes of alkyl radical are in order methyl greater than primary, greater than secondary, greater than tertiary. If more energy is required to form one radical than the other, it means that relative to the alkane from which it is formed, the radical contains more energy than the other and hence is less stable. Thus, it may be concluded that the relative to the parent alkane in each case of the order of stability of free radical is tertiary greater than secondary greater than primary greater than methyl. It must be emphasized that this order is based only on the difference in the energy between the alkyl radical and the parent alkane in each case. As such, it does not reflect the order of absolute stabilities of individual radical. To make this point clear, let us consider the case of methyl radical and ethyl radical, which is the simplest primary radical. The difference in energy between methane and methyl radical, delta H for the reaction CH3H, give rise to CH3 radical plus H radical being 433 kJ is more than the difference between ethane and ethyl radical. Delta H for the reaction CH3CH2 H give rise to CH3CH2 radical plus H radical being 410 kJ. This merely means that the stability of methyl radical relative to methane is lesser than the stability of ethyl radical relative to ethane. Fifth, explanation of relative stabilities of alkyl free radical. First, hyperconjugation. The relative stabilities of alkyl free radical are explained primarily in terms of concept of hyperconjugation. With the exception of methyl free radical, all other alkyl free radical undergo hyperconjugation through overlap between a sigma orbital of alkyl group and a p orbital containing the odd electron. Taking CH single bond C radical to represent an alkyl free radical in general, delocalization through sigma p orbital overlap may be shown as in the adjoining figure. As a result of this overlap, the delocalized electron help in binding together 3 atoms, 2 carbon and 1 hydrogen to some extent. In terms of the resonance, the above situation may be represented by saying that the given alkyl free radical is a resonance hybrid of 2 contributing structures as shown below. This means that CH bond is slightly less than a single bond, while CC bond has some double bond character and the odd electron is partially present on hydrogen atom. The actual number of contributing structure or the extent of delocalization of odd electron depend upon the nature of alkyl radical. The more the number of contributing structures or the more extensive the delocalization, the more stable is the radical. Let us, for instance, compare the relative stabilities of methyl and ethyl radicals. In methyl radical, hyperconjugation is not possible and no delocalization of odd electron take place. But in ethyl radical 1 degree, there is considerable delocalization of odd electron due to contribution from normal structure and 3 hyperconjugation structure as shown below. As a result of stabilization due to resonance or delocalization, ethyl radical is about 25 kJ mole inverse more stable than methyl radical. As we pass on to isopropyl radical 2 degree, it will has 6 hyperconjugation contributing structures in addition to the normal structure as given below. Due to the greater delocalization resulting from more contributing structure, isopropyl free radical is more stable than methyl free radical to the extent of 37.6 kJ mole inverse. Similarly, tertiary butyl radical 3 degrees stabilized to the extent of 50 kJ mole inverse since it has 9 hyperconjugation structure in addition to the usual structure and therefore very extensive delocalization of electron take place. In general, the order of stabilities of alkyl radical is tertiary greater than secondary greater than primary greater than CH3 radical. Second, resonance or hyperconjugation. Like carbocation, the carbanion free radical exhibiting resonance or conjugation are also more stable than simple alkyl radical. For example, allyl free radical is more stable than alkyl free radical because the former is stabilized by the resonance. CH2 double bond CH single bond CH2 resonance sign CH2 single bond CH double bond CH2. Similarly, benzyl free radical is highly stabilized by resonance as shown below. It can be readily understood that triphenyl methyl free radical is very highly stabilized by resonance due to presence of 3-phenyl group attached to carbon carrying the odd electron. Determination of stabilities of some common free radicals of different kinds. The relative stabilities of free radical can be measured by determining homolytic bond dissociation energy of RH bonds. The relative stabilities of some common free radical are given below in decreasing order. CH2 double bond CH single bond CH2 radical is greater than CH3 thrice C radical greater than CH3 twice CH radical greater than CH3 radical CH2 greater than CH3 radical greater than CH2 double bond CH radical greater than benzyl radical greater than benzyl CH2 radical. Carbenes. What are carbenes? Carbenes are neutral divalent chemical species in which a carbon is covalently bonded to the two atom and has got two non-bonding orbital having 2 electron between them. In other words, carbene contains a neutral carbon atom having 6 electron in the valence shell, out of which 2 are unshared. The most common carbene are CH2 methylene and CCl2 dichloromethylene. Carbenes are highly reactive species having very short life period. Second, types of carbene. An interesting feature of carbene structure is that it may exist in two distinct states. First, singlet carbene. There are carbene in which unshared electrons are paired. They are present in different orbitals. Triplet carbene. These are carbene in which unshared electrons are not paired. They are present in different orbitals. For example, methylene carbene can have either of the following two structures depending upon its mode of formation. CH2 singlet methylene unshared electron pair H single bond C single bond H triplet methylene unshared electron not paired. Triplet carbene represent biradicals divalent free radical. Third, formation of carbenes. There are two methods generally employed for the generation of carbene. First, by the thermal or photochemical decomposition of aliphatic diazo compound, ketenes or cyclopropane or oxyrenes for example. Diazomethane in the presence of light or heat give rise to methylene carbene plus N2. Ketene in the presence of light or heat give rise to CH2 carbene plus CO. Phenyl cyclopropane or phenyl oxyrene in the presence of heat or light give rise to CH2 double bond C6H5CH double bond CH2 carbene. Second, by the action of a base on suitable halogen compound. This method is usually employed for the generation of halogen carbenes and the base commonly used is potassium tertiary butyl oxide. For example, chloroform plus tertiary butyl oxide ion give rise to Cl single bond C negative Cl plus CH3 thrice COH. It may be noted that in the above reaction, H positive and Cl negative are removed from the same carbon. It means alpha elimination take place. A well-known example of reaction in which carbene is formed as an intermediate is Reamer-Timmer reaction of phenol to give salicylaldehyde. It involves the formation of dichlorocarbene CCl2 as an intermediate. Phenol plus CH3Cl CHCl3 plus 3KOH give rise to salicylaldehyde plus 3KCl plus 2H2O. Fourth, structure of carbene. In singlet carbene, the central carbon is in the state of sp2 hybridization. On the three sp2 hybridized orbitals, two are used in forming two single bonds with a monovalent atom or group attached to carbon. The third sp2 orbital contains the unshared pair of electrons, while the unhybrid p orbital is empty. In the triplet carbene, the central carbon is in the state of sp hybridization. The two sp hybridized orbitals are used in the forming single bond with the two monovalent atom or group attached to the carbon. The two unhybrid p orbital contain one unshared electron each. Fifth, relative stabilities of carbene and its explanation. It has been found that triplet carbenes are lower in energy than and therefore more stable than singlet carbene. This is because placement of two electrons in a single orbital in a singlet methylene involves electron repulsion energy which must be overcome to pair the two electrons in the same orbital. On the other hand, in triplet carbene, the two electrons occupy different orbitals and the electron repulsion is much less. As a result, singlet methylene have higher energy than the triplet methylene. The difference in energy is about 37.6 to 46 kilojoule mole inverse. Comparison of singlet and triplet carbene. In singlet carbene, two unshared electrons are present as pair in one orbital, whereas in the triplet carbene, two unshared electrons are present as two unpaired electrons in different orbitals, and thus it represents a biradical. In singlet carbene, the relatively are less stable, whereas triplet carbene relatively are more stable. In singlet carbene, the central carbon is sp2 hybridized, whereas the triplet carbene, the central carbon is sp hybridized. Nature of reagent. When two substances react together, one of the substances is regarded as attacking reagent while the other is taken as substrate. The substance which get attacked. The new substance formed as the result of reaction are called products. Thus, the occurrence of a chemical reaction may be depicted as substrate plus attacking reagent give rise to product. It may be pointed out that the term attacking reagent is usually employed for the substance whose presence brings about a chemical change in the given substrate to form the product, but the use of two terms is purely relative. A particular substance may be termed as a substrate in one reaction and an attacking reagent in the other. However, the following conventions are generally followed in the use of the two terms. First, in the reaction between an organic and an inorganic substrate, the organic substance is treated as the substrate while the inorganic substance is taken as the attacking reagent. For example, iodoethane substrate plus attacking reagent is aqueous KOH give rise to 2C2H5OH plus Ki. Second, in a reaction between two organic substances, the substance which implies the carbon atom in the formation of a new bond between carbon atom and a heteroatom is treated as the substrate. The other substance is taken as the attacking reagent. For example, ethanoic acid substrate plus ethanol attacking reagent give rise to new bond formed. Third, in a reaction between two organic substances involving the formation of a carbon-carbon bond, one of the substances is arbitrarily assumed to be a substrate while the other is taken as the attacking reagent. For example, benzene substrate plus ethanoyl chloride attacking reagent give rise to benzene attached with C double bond of CH3 plus HCl. Classification of reagent. There are three types of attacking reagent taking part in the organic reaction. These are free radical. Their formation and relativity has already been discussed. Second, electrophilic reagent. An electrophilic reagent or an electrophile electron-loving particle is reagent containing an atom which is deficient in electron. Because the presence of electron deficient atoms such as reagent tries to seek electron from other sources and thus behave as a lavish acid. It attacks a molecule at the point of higher electron density. Type of electrophile. There are two types of electrophiles. First, positively charged ion or positive electrophiles. Positively charged ions such as hydrogen ion, H positive, hydronium ion, H3O positive, Chlorinium ion Cl positive, nitronium ion NO2 positive and carbocation act as electrophilic reagent. Second, neutral nucleophiles. These are the electrophilic reagent in which the electron deficient atom does not carry any charge. For example, AlCl3, FeCl3 and BF3 belongs to this category. There are certain substances in which the central atom has a complete octet of electron and still it has tendency to coordinate more electron due to the presence of empty d orbital. SnCl4 afford an example of such an electrophile. Carbines also act as an electrophile because the carbon in them has only 6 electrons rather than an octet. Reaction involving electrophilic reagents are known as electrophilic reaction. Third, nucleophilic reagent. A nucleophile reagent or a nucleophilic nucleus-loving particle is a reagent containing an atom having an unshared or lone pair of valence electron. Because of this free pair of electron, such a reagent is in search of a site with which to share an electron and in this way behaves as a base. Lewis concept of bases. It attacks a molecule at the point of a low electron density. For example, consider a OH ion. The oxygen present in the ion contain unshared pair of electron. Due to the resonance, OH ion attack any molecule containing a center of low electron density so as to share the electron at that point. Type of nucleophile. Nucleophile are also of two types. First, negative nucleophile or negatively charged ion. All negatively charged ions such as hydroxyl ion, OH negative, halide ion, X negative, alkoxide ion, RO negative, cyanide ion, Cn negative and carbon ion act as nucleophilic reagent. Second, neutral nucleophile. These are the nucleophile reagent which contain atom and lone pair of electron but do not carry any charge. Water, ammonia and alcohol are neutral nucleophile. Reaction involving nucleophilic reagent are known as nucleophilic reaction. To be precise, all nucleophile and electrophile should be capable of forming covalent bond when they are participate in a reaction. For this reason, positive ions such as sodium ion, Na positive have noble gas configuration are not treated as electrophile because they cannot form covalent bond as they already have noble gas configuration. Classification of organic reaction. The organic reaction may be broadly classified into the following categories. These are: first, substitution or displacement reaction; second, addition reaction; third, elimination reaction; fourth, rearrangement reaction; fifth, isomerization reaction; sixth, condensation reaction; seventh, molecular reaction. First, substitution reaction. A substitution reaction is that which involves the direct replacement of hydrogen atom or some other group of molecule by some other atom or group without any change in the structure of remaining part of the molecule. The product obtained is known as substituent product and the new atom or the group which enter the molecule is known as substituent. For example, when chlorine react with methane in the presence of diffuse sunlight, the hydrogen atom are replaced by chlorine atom one after the other, leading to the formation of the substitution product. CH4 plus Cl2 give rise to methyl chloride plus HCl. Similarly, the reaction of methyl iodide with an aqueous solution of potassium hydroxide to form methyl alcohol is an substitution reaction. For example, methyl iodide plus KOH aqueous give rise to methyl alcohol plus Ki. Substitution reaction may involve free radical, electrophilic or nucleophilic reagent. Accordingly, they can be subdivided as: first, free radical substitution reaction. For example, halogenation of alkane is a free radical substitution reaction. Cl single bond Cl give rise to 2Cl radical. CH3H plus Cl radical give rise to CH3 radical plus HCl. CH3 radical plus Cl single bond Cl give rise to chloromethane plus Cl radical and so on. Second, electrophilic substitution reaction. Nitration and sulfonation of benzene are important example of electrophilic substitution reaction. Benzene plus nitronium ion give rise to nitrobenzene plus H positive removed by a base. Third, nucleophilic substitution reaction. Substitution reaction of alkyl halide are nucleophilic substitution reaction. OH negative plus CH3I give rise to methanol plus I negative. Addition reaction. An addition reaction involves the combination between the molecule of two reacting species substances to form a single compound known as the addition product. One of the reactant in such reaction always contain double or triple bond in its molecule. For example, ethylene plus Br2 give rise to ethylene dibromide. Addition reaction may also involve free radical, electrophilic or nucleophilic reagent. As such, they are subdivided as: first, free radical addition reaction. Addition of HBr to alkane in the presence of benzoyl peroxide is a well-known example of free radical addition. CH3CH double bond CH2 plus HBr in the presence of benzoyl peroxide give rise to N-propyl bromide. Second, electrophilic addition reaction. Most of the addition reaction of alkenes are electrophilic addition reactions. CH3 single bond CH double bond CH2 plus HX give rise to CH3 CH positive single bond CH3 plus X negative. CH3 single bond CH positive single bond CH3 plus X negative give rise to isopropyl halide. Third, nucleophilic addition reaction. Aldehyde and ketone undergo nucleophilic addition reaction. Acetaldehyde give rise to cyanohydrine give rise to H positive acetaldehyde cyanohydrine. Third, elimination reaction. These reaction involves the loss of atom or group of atom from a molecule to form compound containing double or triple bond. Thus, these reactions are essentially the reverse of addition reaction. The common reaction of this type involves the elimination of group or atom from adjacent carbon atom to yield alkene. For example, propyl chlorine plus KOH alcoholic give rise to propylene plus KCl plus H2O. Elimination reactions are further divided into two types as given below. First, unimolecular elimination reaction. These are the elimination reaction in which the rate determining step involves only one molecule. For example, dehydrohalogenation of tertiary alkyl halide usually proceed by E1 mechanism. Tertiary butyl chloride plus alcoholic KOH give rise to CH3 single bond C attached with CH3 double bond CH2 plus KCl plus H2O. Second, bimolecular elimination reaction. These are elimination reaction in which rate determining step involves two molecules. For example, primary alkyl halide such as N-propyl chloride shown above generally undergo dehydrohalogenation by E2 mechanism. Depending upon the relative position of atom or group eliminated, these reactions are also classified as alpha, beta or gamma elimination reaction. First, alpha elimination reaction. These are reactions in which loss of two atom or group occur for the same atom of a substance. For example, chloroform plus OH negative give rise to dichlorocarbene plus H2O plus Cl negative. Second, beta elimination reaction. In these reactions, loss of two atom or group occur from adjacent atom of a substance. For example, ethanol in the presence of concentrated H2SO4 heat करेंगे give rise to ethene plus H2O. Third, gamma elimination reaction. In these reactions, loss of two atom or group occur from alpha and gamma position of molecule, giving rise to the formation of three-membered ring. 1,3-dibromopropane in the presence of zinc dust Freund reaction give rise to cyclopropane plus ZnBr2. Rearrangement reaction. These reaction involves either the migration of a functional group from one atom to other or the complete rearrangement of chain of carbon atom present in the compound to form a new product. For example, 1-bromobutane in the presence of 575 Kelvin AlCl3 give rise to 2-bromobutane. N-butane in the presence of AlCl3 HCl heat in a sealed tube give rise to 2-methylpropane. These rearrangements also take place through the formation of electrophilic, nucleophilic or free radical intermediates. It is interesting to note that the preparation of first organic compound, urea, to be synthesized in the laboratory involved a rearrangement reaction. Ammonium cyanate give rise to urea. Isomerization reaction. These reactions involving the conversion of one isomer into another so that the molecular formula and the carbon skeleton of the reactant end product always remain the same. For example, conversion of trans-2-butane to cis-butane and vice versa is a geometrical isomerization reaction. Trans-2-butane in the presence of light give rise to cis-2-butane. Sixth, condensation reaction. These are reactions in which two or more molecules of the same or different reactant combine to form product with or without the elimination of a simple molecule such as water or alcohol. For example, when acetaldehyde is treated with dilute alkyl, two molecules of acetaldehyde combine to form 3-hydroxybutanol. The reaction is known as aldol condensation. Acetaldehyde 2 molecule plus CH3CHO give rise to 3-hydroxybutanol or aldol in the presence of dilute NaOH. Seventh, molecular reaction. These are the reaction which involves reorganization of covalent bond either intramolecularly or intermolecularly through cyclic transition state under the influence of heat or light. These reactions do not require any catalytic and no ionic or free radical intermediate is involved. These are collectively called pre-cyclic reaction. Electrocyclic and cycloaddition reaction are typical examples of such reaction. First, electrocyclic reaction. These reaction involves conversion of an acyclic dienes to the cyclic alkane and vice versa. For example, buta-1,3-diene in the presence of heat or light give rise to cyclic transition state, give rise to cyclobutane. Second, cycloaddition reaction. These reaction involves addition of two unsaturated molecules of the same or different substance to form cyclic product. An example of this type of is 4+2 cycloaddition reagent given below. The student will come across the detailed mechanism of various reactions at appropriate place in the text. Energy changes during reaction. All chemical reaction involves the breaking and making of bonds. Since energy is required to break a bond while energy is released in the formation of bond, the occurrence of chemical reactions is always accompanied by energy change in one form to another. We will therefore now present briefly certain basic concepts regarding energy change such as enthalpy of reaction, enthalpy of activation, and transition state. First, heat or enthalpy of reaction. Heat or enthalpy of reaction delta H is the total energy change which accompanies the conversion of a definite number of moles as required by the balanced equation of the reactants into the product. It is possible to calculate the enthalpy of a reaction on the basis of bond dissociation energies of various bonds broken and formed during the reaction. For instance, let us consider the following hypothetical reaction. A single bond B plus C single bond D give rise to A single bond C plus B single bond D. Let us suppose that x1, x2, x3 and x4 represent the bond dissociation energy of the respective bond involved in the reaction. During the reaction, two bonds A single bond B and C single bond D are broken while the two new bonds A single bond C and B single bond D are formed. The two bonds broken require a total of energy x1 plus x2 kilojoule mole inverse of energy, while the two bonds formed liberate a total of x3 plus x4 kilojoule mole inverse of energy. Therefore, the total energy change during the reaction, or in other words, heat of reaction, should be x1 plus x2 minus x3 plus x4. It is apparent that if energy consumed x1 plus x2 is more than that of energy released x3 plus x4, there would be overall consumption of energy. The reaction would be endothermic and delta H would be positive value. On the other hand, if energy consumed x1 plus x2 is less than the energy released x3 plus x4, there would be no net liberation of energy. The reaction would be exothermic and delta H would have a negative value. Thus, the reaction between methane and chlorine CH3H 433 kJ plus ClCl 242.5 kJ give rise to CH3Cl 350 kJ plus HCl 430 kJ. Delta H is 433 plus 242 minus 5.5 minus 350 plus 430 is equals to minus 104.5 kJ. Is exothermic reaction since it results in the liberation of 104.5 kJ of energy for every mole of methane converted into methyl chloride. On the other hand, the reaction between methane and iodine is an endothermic reaction. CH3H 433 kJ plus II 151 kJ give rise to CH3I 234 kJ plus HI 297 kJ. Delta H is bracket 433 plus 151 bracket close minus 234 plus 297 bracket close is equals to 53 kilojoule. Second, energy of activation theorem. Collision theory. An important feature of the most of the reaction, whether endothermic or exothermic, is that the reactant acquires some extra energy for the reaction to take place. To understand the reason for this, let us recall that according to collision theory of reactant, the primary condition for the reaction to take place is that the reacting particle must come in contact or collide with each other. But all such collisions do not result in the formation of product. In order to be effective in bringing about the reaction, a collision should fulfill two conditions. The colliding particle must have a certain minimum amount of energy known as threshold energy. Second, colliding particle must be properly orientated with respect to each other at the time of collision. As far as the energy factor is concerned, most of the reactant molecules do not possess sufficient energy in their ground state for effective collision to take place. As a result, when such molecules collide with each other, no bond breaking or making take place and the colliding particle bounce back as such. Therefore, extra stability is needed by the reactant to form the product. The minimum amount of additional energy required by the reactant to undergo effective collision is known as activation energy EA. It is numerically equal to the difference between threshold energy and the ground state energy of the reactant. That is, E activation is equals to E threshold minus E ground state. Most of the organic reactions have activation energy in the range of 40 to 150 kilojoule mole inverse. If the activation energy has a low value, the reaction can take place even at room temperature. On the other hand, reaction with have high activation energy take place only on heating. Energy barrier to the reaction. The concept of activation energy means that the reaction have to be activated or raised to the higher energy level before they form the product. In other words, there exists a certain energy barrier between the reactant and the product in depicting the progress of a reaction. This barrier is generally represented as the energy hump, which has the surmounted before the reaction can be completed. Figure 33.1. It may be compared to the pass on the top to the hill separating two valleys on two sides of the hill. To move from one valley to other, one must move up the hill and cross the pass. Similarly, the reactant must move up the energy level and cross the energy barrier or hump to yield the product. It is interesting to note that even though a chemical reaction involves breaking and making of bond, the two processes are not perfectly synchronized. At the same time, the energy released through bond formation is not completely available for bond fusion. This also explains why the reactant requires extra energy for the reaction to take place. Gibbs free energy change. Gibbs free energy change delta G is very useful parameter for determining the feasibility and direction of occurrence of the reaction. It is related to the change of enthalpy delta H and change in entropy delta S as follows. Delta G is equals to delta H minus T delta S. When all the substances are in their standard state, the relationship may be written as delta G naught is equals to delta H naught minus T delta S naught. The enthalpy term delta G naught is directly related to the bond strength in the starting substances and the product. The entropy, thus delta S naught, is measure of the change in the amount of molecular randomness or disorder caused by the reaction. A reaction takes place in the forward direction only if the negative value of delta G, free energy of the product, is lesser than that of the reactant. On the other hand, a positive value of delta G means that the reaction has a tendency to take place in the backward direction. In case of equilibrium reaction, the equilibrium constant K is related to delta G naught as delta G naught is equals to minus 2.303 RT logarithm of K. Transition state theory. Energy diagram of a reaction. The transition state theory has been very useful in understanding the mechanism of organic reaction and the energy changing take place during the reaction. According to this theory, the reactant do not change directly to the product, but what happens is that when the reactant molecule come in contact with each other, it leads to the formation of highly unstable arrangement of atom whose energy correspond to the energy barrier separating the reactant and the product. The high energy species thus formed is known as activated state or transition state. For example, in the single step reaction represented by the equation A plus B minus C give rise to A bond C plus C. The high energy transition state may be represented as A dotted line, B dotted line, C. The dotted line indicate partial bond. The transition state merely represent a probable arrangement of atoms corresponding to the energy barrier in which a bond is partially but not completely broken and a new bond has begun to form but it's not yet completely formed. It does not represent a substance which can be isolated or even detected. As soon as this transition state is formed, it split into the product. Thus, the complete reaction sequence may be represented as A plus B single bond C reactant give rise to transition state A dotted line B dotted line C give rise to A single bond B plus C product. The free energy difference between the reactant and transition state is known as free energy of activation, denoted as G delta G positive. It determines the rate at which reactant reach the transition state, which in turn determine the rate of reaction. A small value of delta G means that there is only small difference in energy between the reactant and the transition state, and therefore the reaction will take place rapidly. Conversely, a large value of delta G means that the reaction would take place slowly. The transition state is in equilibrium with reactant and its concentration is determined by the equilibrium constant K, which is related to the free energy of activation as delta G is equals to delta H minus T delta S is equals to minus 2.303 RT logarithm of K, where delta H is the enthalpy of activation and delta S is the entropy of activation. Note: the superscript known as double dagger is always used when referring to activation parameter involving the transition state. Figure 2.3 shows the free energy of reactant, transition state and product, free energy of activation, delta G subscript involved in the formation of transition state and the net free energy change delta G naught for a single step reaction. Such a diagram which shows the energy of various species and energy change take place during the progress of reaction from beginning to end is known as energy profile or energy diagram of the reaction. It is to be noted that the reaction energy diagram of all reactions are not similar to figure 3.2. On the other hand, each reaction has its own specific energy diagram depending upon the value of delta G subscript and delta G naught. Energy diagram for multi-step reactions. A reaction can proceed from reactant to product either directly in single step known as concentrated reaction, or take place through two or more steps which include the formation of one or more intermediates. Since the reaction is directly converted into product without the formation of any intermediate substance in a concentrated reaction, the energy diagram of such reaction have only two energy minima corresponding to the reactant and the product, and an energy maximum corresponding to the transition state as shown in figure 3.2. Most of the reaction of organic compound are multi-step reaction involving the formation of one or more reactive intermediates. Therefore, let us now consider the complete energy diagram of multi-step reaction with the help of two-step reaction involving one reactive intermediate. Such a reaction involves the formation of two transition states as shown below. Reactant give rise to transition state first, give rise to reactive intermediate. Step 1. Reactive intermediate give rise to transition state second, give rise to product. Step 2. In such reaction, we draw an energy diagram for such each of the individual step and then join them in the middle as the product of step 1. Reactive intermediate as the starting material for step 2, figure 3.4 and 3.5. Since the intermediate has higher energy than either the reactant or product, it is very reactive and may or may not be isolated. However, unlike the transition state, the intermediate has a measurable lifetime. Depending upon the free energies of activation of the two transition states, the free energy diagram can be of type as shown below. First, if the free energy of activation of transition state 1 is more than that of the transition state second, the energy diagram is as shown in figure 3.3. In such cases, the intermediate readily get converted into the product and can be seldom isolated. The first step of such reaction is the rate determining step of overall reaction. 3.3 Energy profile for two-step reaction in which the first step is rate determining step. Figure 3.4 Energy profile for the two-step reaction in which the second step is the rate determining step. Second, if the free energy of activation of transition state second is more than the transition state first, the energy diagram is as shown in figure 3.4. In such cases, the intermediate is rather stable and can be isolated. The second step of such reaction constitutes the rate determining step of overall reaction. It may be pointed out that for many reactions which we study, the enthalpy changes which take place during the reaction are much larger and more important than entropy changes. Therefore, it is sometimes found convenient to ignore the entropy changes in such reaction. As a result, the reaction energy diagram may be drawn in terms of energy of activation EA in place of free energy of activation delta G subscript. Similarly, the energy change take place during the reaction may be depicted in terms of delta H naught instead of delta G naught. It must be remembered, however, that EA is very close related to delta G subscript and delta H naught is very nearly equal to delta G naught. Figure 3.5 shows the energy diagram of an endothermic reaction in terms of EA, while figure 3.6 shows the energy diagram of an endothermic reaction. It may be noted from these diagrams that first, the difference in energy level between the reactant and the transition state represent the E activation. The difference in energy level between the reactant and the product represent the delta H. Second, for an endothermic reaction, E activation must be at least as large as delta H, although generally it is larger. Third, for an exothermic reaction, E activation may be high or low. Generally, it is on the lower side. Development and structure of transition state, Hammond's postulate. In order to fully understand reaction, it is necessary to completely understand the structure and energy of the transition state which leads to the formation of product. But the transition state has only a transitory existence. As soon as it is formed during the course of a reaction, it changes into more stable species. But it is possible to have an idea of the structure of particular transition state from the reaction energy diagram with the help of Hammond postulate. Hammond 1955 advanced a generalization known as Hammond postulate to correlate the energy and structure of transition state. According to this postulate, structure of the transition state most closely resemble the structure of stable species that lie closest to it in energy. For example, in a strongly endothermic reaction, the energy level of the transition state is much closer to that of the product than reactant. Therefore, the transition state would be expected to closely resemble the product in structure as well. On the other hand, in a strongly endothermic reaction, the transition state is energetically much closer to the reactant than the product. As a result, it has a strong resemblance to the reactant structurally. For a two-step reaction, the first transition state may be structurally resemble either the original reactant or the intermediate, whichever is close to in energy. The second transition state in turn may resemble structurally either the intermediate or the final product, according as which the energetically closer to it. Effect of catalyze on the transition state. Many reactions which we shall study involve the use of some suitable catalyst to increase the rate of reaction. What the catalyst does in such reaction is to provide an alternate path from reactant to product with a lower energy transition state. Thus, the catalyst lowers the energy of activation required for the reaction so that the rate of reaction increases. It must be pointed out, however, that the delta H or delta G for the reaction remain unchanged even in the presence of catalyst. Assigning formal changes or intermediate and other ionic species. While studying the various reaction intermediate, it has been found that these species may either carry positive or negative charge, or they may be neutral in character. In order to predict whether a given species carries some charge or not, we now present a very simple method known as formal charge method for charge explanation or intermediates. Formal charge. It is the amount of positive or negative charge which can assign to certain atom of a species in order to know whether the species as whole carries some charge or not. The calculation of formal charge involves the comparison of the number of valence electron in the neutral atom in the free state and the number of valence electron associated with the atom in the bounded state. The difference between the two values gives the formal charge on the atom in the given species. This is formal charge on an atom in a given species is equals to number of valence electron in the free atom minus number of valence electron in the bonded atom. Calculation of number of valence electron in the bonded state. To calculate the number of valence electron associated with an atom in the bonded state, first, the number of electrons shared between two atoms are divided equally between the two atoms that share them. This means that even though the electrons are shared between the two atoms, it is still thought as if each atom owns one electron to be of the shared pair. Second, the number of non-bonding valence electrons of an atom are assigned exclusively to the atom. The sum of the number of electrons assigned as above gives the number of valence electrons in the bonded atom. This is also sometimes referred to as the average electron. That is, number of electron in the bonded atom or average electron is equals to half into number of shared electron plus number of non-bonding electron. Therefore, the formal charge on a bonded atom may also be expressed as formal charge on atom is equals to number of valence electron in the free atom minus half of the number of shared electron plus number of the non-bonding electron. Formal charge on a species as a whole. Knowing the formal charge on each atom in the given species, the formal charge on the species as the whole can be found by adding together the formal charge on various atoms. That is, formal charge on a species is equals to sum of the total of formal charges on all of the atom in the given species. We now illustrate the complete procedure by considering the example of simplest molecule methane. It is apparent from this structure that carbon is surrounded by 8 electrons which are shared with 4 hydrogen atoms. Therefore, the number of valence electrons associated with carbon in methane is half into 8 is equals to 4. Since the number of electrons in the free carbon atom is also 4, the methane carbon is electrically neutral. In other words, there is no formal charge on carbon atom in methane. We can also arrive at the same conclusion directly. Formal charge on carbon is equals to number of valence electron in free carbon minus bracket half of the number of shared electron plus number of non-bonding electron bracket close is equals to 4 minus bracket start half of the 8 into plus 0 is equals to 4 minus 4 is equals to 0. Each hydrogen atom in methane is surrounded by 2 electrons which are shared with carbon. Therefore, formal charge on each hydrogen is 1 minus bracket start half of 2 plus 0 is equals to 0. Formal charge on methane molecule is equals to formal charge on carbon plus 4 into formal charge on each hydrogen is equals to 0 plus 4 into 0 is equals to 0. It is of course well known that methane molecule have no net electrically charge. Let us compute the formal charge on some of the intermediate already studied. First, free radical. It has been stated earlier that free radical are electrically neutral species. To justify this, let us consider the methyl radical, which is simplest free radical. The carbon is surrounded by 6 bonding electrons shared by 3 hydrogen and 1 non-bonding electron. Each hydrogen is surrounded by 2 shared electrons. Therefore, formal charge on carbon is equals to 4 minus bracket start half of 6 plus 1 is equals to 0. Formal charge on each hydrogen is equals to 1 minus bracket start half of 2 plus 0 is equals to 0. Formal charge on methyl radical is formal charge on carbon plus formal charge on hydrogen is equals to 0 plus 3 into 0 is equals to 0. Second, carbocation. The positive charge on the carbocation may be verified by considering the case of methyl cation. It may be easily seen that formal charge on carbon is 4 minus half of 6 plus 0 is equals to plus 1. Formal charge on each hydrogen is equals to 2 minus half of 2 is equals to 0. Therefore, formal charge on carbocation is equals to 1 plus 3 into 0 is equals to 1. Third, carbanion. It is well known that carbanion are negatively charged species in which the carbon atom carries negative charge. To rationalize that, we may consider the structure of methyl carbanion. Formal charge on carbon is equals to 4 minus half, bracket start, half of 6 plus 2 is equals to minus 1. Formal charge on each hydrogen is equals to 1 minus, bracket start, half of 2 plus 0 is equals to 0. Therefore, formal charge on carbanion is equals to minus 1 plus 3 into 0 is equals to minus 1. Fourth, carbenes. The simplest carbene is methylene. Formal charge on carbon is equals to 4 minus, bracket start, half of 4 plus 2 is equals to 0. Formal charge on each nitrogen is equals to 1 minus, bracket start, half of 2 is equals to 0. Formal charge on carbene is equals to 0 plus 2 into 0 is equals to 0. Carbenes are neutral species. Fifth, nitrines. The neutral character of nitrene may be verified with the formal charge calculation on methyl nitrene. Formal charge on carbon is equals to 4 minus, bracket start, half of 8 plus 0 is equals to 0. Formal charge on nitrogen is equals to 5 minus, bracket start, half of 2 plus 4 is equals to 0. Formal charge on each hydrogen is equals to 1 minus, bracket start, half of 2 is equals to 0. Therefore, formal charge on nitrene is equals to formal charge on carbon plus formal charge on nitrogen plus 3 into formal charge on hydrogen is equals to 0 plus 0 plus 3 into 0 is equals to 0. Thank you.